Okay, I believe we should start. Well, today I want to cover a completely new subject. I want to discuss something what is called Gröbner basis. So let me explain briefly what we're going to do during the next lectures, several lectures. Well, first of all, until right now, we have studied only polynomials in one variable. Well, now I want to deal with polynomials in several variables. So what is good about polynomials in one variable? We have Euclidean division algorithm. The Euclidean division algorithm allows us to solve like any problem related to polynomials in one variable. So when we switch to polynomials in several variables, we do not have such an algorithm. You can even rigorously prove that there is no analogy of the Euclidean division algorithm in some way. However, we still want to compute efficiently with polynomials in several variables. And there is some way to do that. So we can actually provide some algorithm which is very similar to the division algorithm. And we will discuss this algorithm and its properties during the lectures. Okay, so but before we start, let's fix the context. So first of all, I will assume that f is a field. Well, now I want to fix several symbols. x1, xn are just symbols or variables, if you wish. And what is a polynomial in several variables with coefficients in f? Well, it's a picture of the form like this. So let me write down the expression, and then I will explain what's going on here. So we multiply variables and then multiply each variable by a coefficient. So this expression is an element of f. And we have only finitely many summands. So only finitely many coefficients are non-zero. So we have finitely many summands here. Finitely many are not equal to 0. So this is a polynomial in several variables. Well, for example, we may have something like this. Like 1 over 2 x1 squared x4 plus 3x2 minus 7x5 to the 8. So this will be an example of a polynomial in like 5 variables, x1, x2, x3, x4, x5 with rational coefficients. So here the field is Q. Okay, and this one is 8. Okay. Well, I believe you already know all of this, but I just want to fix some notation and be general at the beginning. So the degree of a monomial, so a monomial is an expression of this form, just the product of variables, and by the definition, the degree, or the full degree, is just the sum of the degrees of the variables. And if we want to define the degree of a polynomial, so if we have a polynomial f, the degree of a polynomial f, well, let's say let's do it like this. So if we have a polynomial of this form, so the degree is the maximum of the degrees of its monomials, where the corresponding coefficient is not 0. So this is the definition of the degree of a polynomial. So we consider all the monomials inside the polynomial and compute the degree of each monomial, and then take the maximum. And the degree satisfies the usual property. Yeah, by the way, this definition doesn't work in case of the 0 polynomial, because the set of monomials there is empty. So by the definition, we define the degree of the zero polynomial to be minus infinity. As usual, each constant has the degree 0 except for the zero polynomial. And the degree satisfies the usual property. If we multiply polynomials, then we have this. I just don't want to discuss all these details. I think it should be clear. What is important, well, now the degree is not a linear order on the set of all monomials. For example, if we have a polynomial like this, well, the degree of x is 1 and the degree of y is 1. So the degree doesn't allow us to say which one is higher. So which one is larger? Is x is larger than y or y is larger than x? And if we want to define some analogy of a division algorithm, then we need to explain which monomials are higher than the other ones. In order to do this, the degree is not enough. So we need to define something, something better than just a degree. And what we actually need is called a monomial ordering. What is this? Okay, well, there are a lot of ways to define a monomial, well, monomials orderings, and there are a lot of different monomial orderings, but I just want to define a specific set of orderings. So suppose we, oh yeah, and by the way, I forgot to mention that I will denote all the polynomials with coefficients in the field f by f of x1, xn. So this will be the name for all polynomials with coefficients in the field f. So I suppose that f is a field, and this will be all polynomials with coefficients in f, in variables x1, xn. And yeah, now I want to define, yeah, what are monomials? Monomials in variables x1, xn is just the set of these guys. And now I want to have a linear ordering here, a linear order. So how do I define a linear order here? A definition. First, well, I will define a family of lexicographical orders. Now, first of all, I need to specify the order of variables. So first of all, fix an ordering like this. I would say that x1 is higher than x2, it's higher than x3, etc. It's higher than xn. Here I have like n factorial options. So you may choose any other way to arrange them. So, but for simplicity, I just want to use this one. Then, since we know how to order all the variables, I can order all the monomials. And I want to define a lexicographical order. So this will be a lexicographical order. So what is the lexicographical ordering? It's a way to compare two monomials. So how does it compare to monomials? So I need to provide you with a procedure. So suppose we're given two monomials like this, x1 to the k1, x2 to the k2, xn to the kn, and the other monomial is x1 to, let's say, m1, x2 to the m2, etc., xn to the mn. So we have two monomials, and now we want to compare them. First of all, I need to rewrite these monomials in the form such that the highest variable is on the left, the next highest variable is the next one, etc., etc. Since I fixed this specific ordering, well, we already have this property. So x1 is the highest, the next one is x2, the next one is x3, and so on. So I just want to write them from highest to the least, from the left to the right. And now Here is the procedure how to compare these two monomials. First of all, I need to compare the degree of the highest variable. So let's compare K1 and M1. We have several options. The option number 1, K1 is strictly smaller than M1. In this case, we say that the left monomial is strictly smaller than the right monomial. So let me give them names. So let's say this is T1 and this is T2. So if K1 is strictly smaller than M1, we say that T1 is strictly smaller than T2. Well, the other option is K1 is strictly larger than M1. In this case, we do the opposite. And the third option is when K1 is equal to M1. In this case, we need to switch to the second variable and compare the degrees of x2. So in this case, we start comparing K2 and M2. And here we have three options again. Either K2 is smaller than M2, or K2 is greater than M2, or they are equal. So in the first case, again, we say that T1 is strictly smaller than T2. In the second case, we say that T1 is strictly larger than T2. And in the third case, we go to the next variable, and so on. So in such a way, we go through all the degrees of all the variables, and we can compare to any two monomials. So this is how the procedure works. So let me formulate a formal definition. So this is the way how to describe, how to compare two polynomials in an algorithmic way, but let me reformulate this in a way of a statement. So it could be useful. So I will say that a monomial like this is strictly larger than the monomial like this if and only if there exists an index j between 1 and n such that the degrees for all the variables with the index less than j are equal. So K1 is equal. Oh, I'm sorry. I have exactly the same letters here. That's definitely a mistake. There must be m here. I want to consider different monomials. So for all variables with indices strictly smaller than j, we have equality, and kj is strictly larger than mj. So when the left-hand side monomial is strictly larger than the right-hand side monomial, well, it happens if and only if, well, for several variables at the beginning, we have exactly the same degrees, and then for some variable j, its degree is strictly larger on the left-hand side than on the right-hand side. So this is how to compare two different monomials. Just in case, there are several examples. So let's say I take q of x, y, z. So if I want to specify an lexicographical ordering, first of all, I need to specify the order of the variables. So let me say x is greater than y is greater than z. So now this allows me to define the lexicographical ordering like this. And this one knows how to compare monomials. And for example, x squared z will be strictly larger than xy cubed, and this one is strictly larger than x z to the 5. So let me explain why, just in case. So when you compare these two, first of all, you need to check the degree of the largest variable. So the largest variable here is x, and here x has degree 2, and here x has degree 1, so this one is larger. Now, if you want to compare these two, first of all, you need to compare the degree of x Well, here the degree of x is 1, and here the degree of x is also 1. Well, we need to switch to the next variable, and the next variable is y. Here, the variable y has degree 3, and here, well, here what is written is y to the 0. So the degree of y here is 0. So 3 is larger than 0. So we do not compare y and z. We compare y here and the degree of y here and the degree of y here. So here is 3 and here it's 0. So that's why this one is larger than this one. So this is how you compare different polynomials. Okay. So that was the definition of a lexicographical order, and an example with 3 variables. Just in case, are there any questions regarding the procedure? Okay, so let's move on. Now I want to discuss some properties of this ordering. So, remark. Well, suppose we have monomials in n variables, and we have any lexicographical order. This means that I don't care about the order of the variables. So lex is just any of them. So we have like n factorial lexicographical orderings. So I just take any of them. So the property number 1, well, we have this monomial. 1 is the monomial where the degree of each variable is just 0. So this is also a monomial. So y belongs to this set. Just don't forget about this. And suppose that m is any other monomial which is not equal to 1. Then 1 is always strictly smaller than m for any monomial m. So this is the smallest possible. The property number 2, if one monomial m prime divides the other monomial m, well, in this case, we can represent m as the product of t and m prime, where t is also a monomial in variables x1, xn. So in this case, monomial m prime is not greater than monomial m. And if t is not equal to 1, which means they are different, this is exactly the same as saying m prime is not equal to m. In this case, m prime is strictly smaller than m. So this is a linear ordering. So this ordering is finer than the ordering given by the division procedure. And what I want to say next, and the later property is this. So if m prime is not greater than m, and t is any monomial, then m prime t is not greater than mt. And if we have a strict relation here, then exactly the same relation happens here. So if m prime is strictly smaller than m, then m prime t is strictly smaller than mt. So this is how the product of monomials is related to the ordering. So it respects the ordering. So these are some simple properties that you should keep in mind. So okay, what do we have now? So now we know the way how to compare any two monomials in several variables. Okay, and before doing anything fancy, I want to prove that this ordering is actually good in some way, in some sense. So let me explain what does it mean that we have like a good ordering. So I would like to formulate this as a claim. Well, suppose we have this set of monomials in several variables. These are monomials. And we fix any lexicographical ordering, like any. So, this pronoun any means that we have like any ordering, any ordering of the variables. And suppose that we have a sequence of monomials, strictly decreasing sequence of monomials, f1, m1, m2, m3, etc., where all these guys are just monomials. And this is a comparison with respect to this ordering. What I'm saying that such sequence is always finite. Then this sequence is finite. So there is no infinitely long decreasing sequence of monomials with respect to any lexicographical ordering. So if you have a decreasing sequence, strictly decreasing sequence of monomials, at some step you must stop, and you will not be able to find a smaller monomial in your sequence. So this is how it works. So are there any questions regarding the claim? Oh, just in case, could you write plus in the chat if you can follow me? I just need some feedback, just in case. Okay, so yeah, since there are no questions, it's a bit intriguing.
Like we had some similar theorem on discrete math.
Oh, okay, then it's cool.
Not theorem, but it wasn't. Yeah,
Remark.
you said that it's in the beginning of the course, almost.
Oh, okay. So, but just in case, do you know how to prove this claim? Okay,
Yes.
so oh, you know how to prove this. Is there anyone who doesn't know how to prove this? It doesn't mean that I won't prove this, but I just want to know, is there anyone who doesn't know the proof?
I guess it can be done by induction, some sort of.
Okay, let me show you the proof. It's actually really obvious how to do this. So suppose we have these decreasing sequence of monomials. So what does it mean? It means that we have expressions like this. This index is the index of the monomial. So here we have x1, k1 of 2, x2, k2 of 2, etc., kn, kn of 2, and so on. Okay. Now, if the first one, so let's take a look at the first variable here. So since m1 is strictly larger than m2, then we have only two options for k1 of 1 and k1 of 2. The degree here must be equal or greater or equal than the degree here. Well, why? Well, because if it's strictly smaller than this one, then we obviously have a different ordering here. So this is what we should have here. So, and as you can see, now for all the degrees for the first variable, so let's say here we have something like mk. Oh, not mk, let's say mr. So here we have these property. But these numbers are just natural numbers. And this is non-increasing sequence of natural numbers. If we have non-increasing natural numbers, well, it must stabilize at some point in the sense that there is index r such that all the numbers beginning from this one must be the same. So for starting from this point, k1 of r doesn't change. The degree of x1 doesn't change. So everywhere here we will have equality for the first degree. Why? Because, well, there are finitely many integers between 0 and k1 of and the first degree here. So such moment must exist. So this is the minimum in the sequence. Okay, but then since we have strict strict relation here between MR and the next one, this means that we need to compare these monomials by the next degree. So we take a look at these guys. So here we have k1 of r, which is the same, and we can repeat the arguments for the next variable. So if these degrees are exactly the same and this guy is strictly larger than this guy, then for these 2 degrees we have this relation. So it cannot be in the other way around, otherwise this one would be smaller than this one. And again, we may find some step, let's say R2, well, R1, oh no, I believe R2 is better, such that starting from these monomial, the degree of the second variable doesn't change. So here it's exactly the same. So now, so here we have this relation, and then all the in this sequence, the degrees of x1 and x2 are exactly the same. So we may proceed, and after finitely many steps, we will prove that at some point, the degrees of all the variables must be the same. This means, starting from this point, all the monomials are the same. So the sequence is no longer strictly decreasing. So this is how you do this. Just in case, are there any questions? Okay. But I just want to be clear that the absence of strictly decreasing sequences is a very tricky property. For example, if you take the polynomial ring with 2 variables, x and y, and you take x to be larger than y, then x squared y is strictly larger than xy to the n for any natural n, just by definition, because if you consider the degree of x, here it's 2, here it's 1, so all these monomials are strictly smaller than this guy. So there are infinitely many monomials smaller than the fixed monomial, but there is no infinite decreasing sequence of the monomials. So the absence of infinite strictly decreasing sequence of monomials doesn't mean that you have finitely many monomials smaller than a fixed one. So, okay, so as you can see, we have infinitely many. But if you want to produce a sequence, you need to choose at least one of them to be the second monomial. And when you choose a specific number n, like n0. And then there are only finitely many powers smaller than n0. So you will not have an infinitely decreasing sequence. So you have infinitely many smaller than your fixed monomial, but you don't have an infinitely decreasing sequence. So these are a bit different properties. Just in case, Kirill, do you have a question?
No.
Okay. No? Oh, okay. Okay, now we're ready to define a reduction process. Okay. So now we know how to compare monomials in a polynomial, and we want to define a reduction process for polynomials. Well, now suppose f is a field. F of x1, xn is the polynomial ring, I'm sorry, in n variables. And we fix a lexicographical ordering. And suppose f is a polynomial here. Well, when f is a non-zero polynomial, we can represent it in the following form. Let me write it down, and then I will explain the meaning of all these symbols. So here, Ci, C2, and Cr are coefficients. So these are coefficients in f. And M1, M2, Mr are monomials. So I just don't want to write explicitly that M1 is x1 to the k1, x2 to the k2, etc., etc. I just want to denote the monomials like this. So each polynomial is just a sum of monomials multiplied by coefficients. Moreover, we can choose, in this case, the monomials M1 and 2 Mr in such a way that M1 is the highest possible monomial, then M2 is the next highest possible monomial, etc., and Mr is the lowest possible monomial. So because we know how to order all the monomials, we can choose the largest one here, and actually we can linearly order all the monomials in a polynomial. So here we have two parts of this polynomial, this blue part and this red part. The blue part is the leading part, this is the leading term. I will denote it by T1 of f is C1 times M1 is the leading term. Then C1 of f is just C1 small, is the leading coefficient. Is the leading coefficient, and M1 of f is just M1 is the leading monomial. And this part, the red part, I would like to denote it by f0 is the tail of the polynomial f. So now, since we have a lexicographical ordering, we can divide each polynomial into the leading term and the tail. So now I'm ready to define elementary reduction. So what is an elementary reduction? Definition. Okay, so we have a polynomial f, come on, a polynomial f, and another polynomial g. And we assume that g is not zero. Now I want to define an elementary reduction of a polynomial f with respect to g. Okay, well, suppose there is a monomial of f which is divisible by the leading monomial of g. such that the leading monomial of G divides M. So this is the information that I need. So we have a polynomial G, F, we have a polynomial G, which is non-zero, and we need to fix a monomial M of the polynomial F, such that this monomial of F is divisible by the leading monomial of G. Oh, I need to write M1 here, by the leading monomial. So in this particular case, we can rewrite M in the form T times M1G, where T is also a monomial in variables x1, xn. So I just need this notation. So now I define a reduction. So let me write it like this. So our polynomial f is in the form c1 m1 plus etc. plus cr let's say r mr plus etc. plus ck mk, and g is in the form let's say c1 of g m1 of g plus g0, which is the tail. And let's suppose that this polynomial is actually m. So this is our m. So this guy is divisible by the leading monomial of g. So what do I want to do now? So I want to multiply the second polynomial by t, and then I want to fix the coefficient such that it becomes CR, and then subtract from f g multiplied by all these factors. And then I can kill this summand and replace it by the tail of g multiplied by something. So what I do, let me define f minus CR over C1 of G times T times G. So this will be f prime, and f prime is by definition is an elementary reduction of f with respect to G. This guy is elementary reduction of f with respect to G. So this is just the definition. So let me go again one more time. So we have two polynomials. We fix a monomial in one of them such that this monomial is divisible by the leading monomial of the other one. And then we subtract from f g multiplied by this expression. And if you can take a closer look at this expression, you'll see that the leading monomial of this expression is exactly, well, the leading term of this expression is exactly CR times MR. And after this procedure, we just kill this summand and replace it by a sum of smaller monomials. And this is the elementary reduction. So let me show you an example, just in case. An example. So assume that we have a polynomial ring like this, and x is larger than y, and we fix the lexicographical order with respect to this ordering of variables. Now I would like to take f to be x cubed y plus 2xy to the fourth plus 3, and let's say g be xy cubed minus 1, something like this. Okay, now this is the leading monomial of g, and the leading coefficient is 1. Let me take m to be this 1. Well, this is the only monomial divisible by the leading monomial of g. So this is your m from the definition here. So we have m1 of g is equal to xy cubed, m is equal to xy to the fourth. So t is equal to y. So T is the multiple that is needed to get M from M1G. And now what I'm doing, I need to write this expression 2T minus G. And let's see what happens here. We have this, which is F minus 2y, and here we have xy cubed minus 1. And as you can see, this guy multiplied by this expression is equal to minus this guy. So we can cancel these ones, and the result will be x cubed y plus 3 plus 2y. So this means that the later polynomial, which is f prime, is an elementary reduction of f with respect to g. Okay, so that was a demonstration of the definition here. So we can reduce each polynomial by any other one. Just in case, are there any questions regarding the definition of an elementary reduction? Okay, so now I can define a reduction with respect to a set. So in the case of polynomials in one variable, we always divide a polynomial with respect to a polynomial. But here we can divide a polynomial with respect to a set of polynomials. So let me show you this. Sorry. Okay, so suppose the definition. Well, suppose we have two polynomials, f and f prime are polynomials in our polynomial ring. Well, as usual, f is a field and we have a lexicographical ordering. So is a field and we have some lexicographical ordering. So in order to reduce something, we need to fix an ordering. And suppose G is a set of non-zero polynomials. It's just any set. It could be infinite, it doesn't matter. So we will say that f is reducible to f prime with respect to G if we have a sequence of elementary reductions of the form. We can, oh yeah, and I didn't write the notation. I didn't explain the notation. Well, when I write something like this, it means that f1 is an elementary reduction of f with respect to G1. So here we have something like this. Okay, so let me repeat. So we have two polynomials f and f prime, and we have a set of non-zero polynomials. We say that f is reducible to f prime with respect to g if we have a sequence of elementary reductions where the first polynomial is f and the later one is f prime, and all the polynomials g1, g2, gk belong to g capital. So if we can reduce f to f prime, this simply means that we, oh, what happens here? It simply means that we can divide f several times by the elements of G, such that at the end we will get f prime. So this is the definition of an elementary reduction, of the reduction. And in this case, we will write this picture to say that f is reducible to f prime with respect to G. Okay, and now I want to define the notion of a remainder. So now I describe the process of division of a polynomial with respect to a set of polynomials. But what do we call a remainder? definition. Well, suppose we have a polynomial f here, and we have a set, and we have a set of polynomials, non-zero polynomials. Then we will say that f is a remainder if every monomial in f is not divisible by a leading monomial of any polynomial in G. So it's impossible to make a step of an elementary reduction. So it's impossible to make an elementary reduction of f with respect to any element of G. So let me repeat. So if for any monomial of f is not divisible by m1 of J for any J in G capital. So you cannot reduce this polynomial even once. In this case, we will say that f is a remainder with respect to G. So you cannot reduce it even further. Okay. So this is very similar to what we have in case of one variable. But the important difference here is that, well, actually, the remainder is not uniquely defined. If we start dividing a polynomial, we may get two different remainders. So let me show you an example. So a remark, what may happen, you take a polynomial, you have this set G, and then you may start the process of reduction, and you go one way, and at the end, you get some polynomial R1. Or then you may start this process in a different way. Let's say you use different polynomials from the set G, or you use different order or something like this. You will get a different sequence here. And at the end, you may get a completely different polynomial. So all R1 and R2 will be remainders with respect to G, but it may happen that they are different. So it may happen. This need not to happen, but it may happen. And here is an example. I just want to give you an example. Well, let's take Q of x, y, z. We used the lexicographical order where x is greater than y is greater than z. And in this case, we take f to be x, y, z. And G capital will be the set consisting of xy minus 1 and yz minus 1. So this is G1 and this is G2. So let me underline the leading terms, which are exactly the leading monomials of these polynomials. So you can do a reduction of xyz with respect to G1. So how do you do that? You take xyz and you subtract z times G1, which is xy minus 1. And here, as you can see, you cancel the only monomial in f, and the result will be z. And now z is not divisible by the leading monomials of the polynomials in G capital, so it's a remainder. But now you can do the same procedure, but using G2 instead of G1. Then what you do, you take xyz and subtract x times yz minus 1, which is G2. And as you can see, the result will be x, and x is also a remainder. And now we see that x and z are different polynomials. So these are two different remainders with respect to G. So it may happen that the same polynomial may have different remainders with respect to a specific set G. Well, the reason why it happens is because G is a bad set. So somehow we can change the situation if we choose a different subset G. But here, as you can see, we may have a good subset or a bad subset in the sense that if we are given a good subset G, then it may happen that all the remainders are the same, and if we're given a bad subset G, it may happen that, well, some polynomials may have different remainders. So here we want to give a definition. Well, instead of saying that a subset G is good or bad, we just give the subset a name, and the name is the Grobner basis. So the definition, well, if we have a polynomial ring with a fixed lexicographical ordering, and suppose G, let's say G is a subset of non-zero polynomials, then we say that G is the Grobner basis if every polynomial has a unique remainder with respect to G. Okay, this means that if you take any polynomial and you start the division procedure, the reduction procedure, you will always get exactly the same remainder. So you may have different amount of steps. You may have many different intermediate polynomials in each procedure, but the result must exist, so the process always stops, and the result of the reduction will always be the same. So if this happens for every polynomial f, then this set is called a Grobner basis. So well, currently it's clear it's a good idea to have a Grobner basis because the division procedure has a uniquely defined remainder, but it's not clear how to check if a subset is a Grobner basis or not. So later on we will see several criteria how to check if something is a Grobner basis or not. But currently I just want to give you several examples without any proofs, just because I want you to know well, that Grobner basis exist, because currently it's not clear even if we have at least one Grobner basis. It could be that like every subset is just bad and we do not have Grobner basis at all. But actually there are a lot of Grobner bases and we will see why. But currently, suppose G is a subset consisting of one non-zero polynomial. Then this set is always a Grobner basis. A Grobner basis. So I'm not proving this currently. We will prove this later. But what I'm interested in now is that the fact that if you have a set consisting of just one polynomial, it's always a good set. So if you divide with respect to one polynomial, the remainder will always be correctly defined. It will always be unique. The second part, the second example, let me be more precise. Let's take something like x, y, z, w, and let's take any lexicographical ordering. Let's say x is higher than y, is higher than z, is higher than z is higher than w, and then I want G to be this set xy minus 1, zw minus 1. So as you can see, the leading monomials are coprime, so they do not have a common factor. So in this case, your set is also a Grosvenor basis. This is a Grosvenor basis. So we will see in the next lecture why this is true. But now it's just an example without proof. So one can show that this is also a Grosvenor basis. Okay, so it may happen. So what next? Well, now there is an interesting question that I didn't address. You see, when I say that we have a Grosvenor basis, I'm saying that the division process halts, always halts, and the remainder is unique. So, well, a remark. So if we have a polynomial here and a subset here, and we have a fixed lexicographical ordering, then the first question we should ask is this. Suppose we start division of f with respect to g. What do? We do one elementary reduction and we get f1. Then we do next elementary reduction and we get f2, and so on. The process is, does this process stop? Is this true that this process halts? Well, and is this, well, does it depend on the choice of G or F or something like that? Well, what happens is actually this process always halts. And it doesn't depend on the choice of F and G. So for any F and any G, such process halts. And I want to prove this. Well, I don't have enough time to prove this today, but I just want to start some preparations for doing that. So what I'm going to do next, so the next, I'm to show that this procedure always stops. Okay, in order to do this, I need, well, here is an idea how to prove this. Currently, we know how to compare variables and the monomials, but we don't know how to compare polynomials. If I defined a way how to compare polynomials, and I prove that when we apply elementary reduction, the polynomial becomes strictly smaller, like f1 is strictly smaller than f, f2 is strictly smaller than 1, then it's enough to show that every strictly descending chain of polynomials stabilizes. Well, or halts, whatever word you wish. So, and this is the plan. So first of all, I want to define the way of ordering polynomials. Well, okay, so how do I do that? Well, definition. Well, suppose we have two polynomials, f and g. Now I can represent the, yeah, and I have a lexicographical ordering here, like any. In this case, I can represent f in this form, where ci are coefficients and mi are monomials in variables x1, xn. And then I can represent g in a similar form, like a1, n1. Oh, n is not a good choice, which letter to use. Let's say u1, plus etc., plus a d u d. Okay, and yeah, and I forgot to mention that I want to order these monomials in the way m1 is strictly larger than m2 is strictly larger, etc., and then mr. And here are also ai are just the coefficients, ui are monomials in variables x1, xn, and they form strictly descending chain of monomials. And as you can see, we may have different amount monomials here and here. Okay, yeah, and here is the third definition. So in this case, I will, well, we already have the notation. This part is called T1 of f. This part is called C1 of f. And this part is called M1 of f. So you may extend this definition to all the other terms. So for example, T2 will be the second term, T3 will be the third term, etc., etc. So let me write this down here. So Tk of f will be Ck times Mk, and Ck of f will be just Ck, and Mk of f will be just Mk. So this is these are the components, and the definition works only if k is between 1 and r. So I cannot define the term tk of f for k greater than r because I do not have summands greater than r. Okay, so let me, as I can see, I have like, by the way, am I right that I have like 5 minutes left, or I have minus 5 minutes? Guys, could you tell me?
We need to check the timetable. 1 second.
No, you have 15 minutes.
15.
Oh, 15 minutes. Oh my God, that's incredible. I have like infinite amount of time. I can like prove almost everything that I want. Cool. So yeah, that probably was a mistake to introduce the polynomial g here. So what I'm saying now, well, let me explain the philosophy of what's going on here. So you can compare these two polynomials by the sequence of monomials. Like this one is larger than this one if m1 is larger than u1. If m1 is smaller than u1, you want f to be smaller than g. And if m1 and u1 are the same, you just compare the next monomials. Well, strictly speaking, this procedure doesn't allow you to compare the polynomials because, well, one polynomial could be larger than the other one. For example, what happens if you have like more summands here than here, or what happens if the monomials are the same but the coefficients are different. So it's a tricky question how to compare polynomials. But still, this is the mentality how I should think of this, of what's going to happen. So this is how I think of polynomials, how to compare them when I prove something. But strictly speaking, what I really need is this notation. I just want to order all the terms, and T1 will be the first, the largest term, T2 will be the second largest term, etc., etc. Okay, so now claim. Oh, by the way, I believe I should go up. Yeah, I should go up. Okay. Sorry. Now, the claim. Well, suppose, well, as usual, we have our polynomial ring with fixed lexicographical ordering. And suppose we have three polynomials, f, f prime, and g. And f is reduced to f prime with respect to g So f prime is an elementary reduction of f with respect to g. And now suppose that m1 of f is exactly the same as m1 of f prime, etc. mk minus 1 of f is exactly the same as mk minus 1 of f prime. And also there exists mk of f in f, and there exists mk of f prime in f prime. Then the claim is that mk of f must be greater or equal to mk of f prime. So this is the claim. This is just some auxiliary claim that I need to use in the proof. So let me show you what's going on here. Well, let me write the polynomial f. We can write it like this. So these are the first k minus 1 terms. So so this is m1 of f and mk minus 1 of f, and this is mk. So now we know that f prime is an elementary reduction of f. So we know that when we reduce f with respect to g, we will get f prime. So what does it mean? By the definition of the elementary reduction, we need to take just one monomial here and cancel the corresponding term by the polynomial g multiplied by some coefficient and some monomial. Well, we have several options, like which monomial to choose. For example, it could be a monomial here, it could be a monomial here, or it could be a monomial here. But you see, if we take a monomial here and reduce, let's say we take m2 and reduce with respect to g, it means that f prime, m1 of f prime will be the same, but m2 of f prime will be strictly smaller than f2 of f. So we cannot take any monomial here because of these conditions. So because of these conditions, the reduction happens here or here. So we have two options. The option number 1, we reduce this guy, or we reduce something here. This is the option number 1. This is the option number 2. You see, if we reduce this monomial, we replace this monomial by the sum of strictly smaller monomials coming from the tail of G. In this case, okay, let's consider the case number 1. In the case number 1, f prime will be c1 m1 plus etc. ck minus 1 mk minus 1 plus something which is different from, I mean, in this case, and here we do not have ck mk because it's reduced by g in the process of elementary reduction. So here we have something, and this something is either came from the result of reduction here, or from some of the monomials here. So this guy is either here or appears here at the process of the reduction. In any case, by the definition of the reduction, this monomial must be strictly smaller than mk. So this guy will be strictly smaller than mk. So in this case, this guy is mk of f prime. So this is just by definition mk of f prime. This is the kth highest monomial, and mk is by definition is mk of f, And in this case, it's strictly larger than mk of f prime. So in this case, we're done. In the second case, if we have the second case, f prime will be of the form c1 m1 plus etc. ck minus 1 mk minus 1 plus ck mk plus something here. So because since we reduce a monomial here, it can be replaced. Well, it will be replaced by a sum of smaller monomials. So we will not change the kth highest monomial in the polynomial f. So in this case, the, mk will be kth highest monomial in f prime. So in this case, it will be exactly the same as the monomial in f. So in the second case, we get the equality of the kth monomial. So, and we're done. So this is how it works. Just in case, are there any questions regarding the proof? Should I clarify any detail here? Yeah, okay. And now let me try to prove the halting result. So now I want to prove that the halting process stops. The reduction, I'm sorry, the reduction process halts. Yeah. What happens when we are tired? The claim. Well, suppose we have our polynomial ring, we have a lexicographical ordering, then for every polynomial here, and for every set of non-zero polynomials, the process of reduction, any process, and so we take any reduction process, so we just do it in any order using any polynomials, like in the way we like literally just take any reduction process. So the claim, this reduction process halts. So it must stop. At some point, we will get a polynomial which is a remainder. And we can no longer reduce it by any polynomial of g. So let's do this. How do we prove this? Suppose that the contrary holds. Suppose contrary. So we have an infinitely long sequence. So this is f is the f1. So we have like infinitely long sequence of reduction. And I want to get a contradiction. So how do I get this? First of all, let's write our polynomials in this form. This is the first polynomial. Well, then what is, let me write index 1 here. Then the second polynomial can be also written in this form. Yeah, there are a lot of indices. I hope it's not that terrible here. So well, let's see what happens with the first monomials in this sequence, like everywhere here. Well, let me be more precise. I'm going to consider the first monomials, not terms, but the monomials. So I want to consider the sequence, the first largest monomial of f1, then the first largest monomial of f2, then the first largest monomial of f3, and so on. I'm saying, so my claim is that we have this inequality between the leading monomials. So why? Well, you see, if we have a reduction from f1 to f2, elementary reduction, then we reduced a monomial. if we didn't change the first monomial, then it will be exactly the same here, because if we reduce something here, we do not touch the largest possible monomial, so it will be exactly the same on the second step. But if we reduce the largest possible monomial, we replace it by a sum of smaller monomials. So the leading monomials here must be strictly smaller than the leading monomial on the previous step. So in any case, we have that the leading monomial of F2 will be not greater than the leading monomial of F1, and so on and so on. So we have these descending sequence of the leading monomials of all our polynomials. But by the previous claim, we know that every strictly descending chain of monomials halts. But this one is infinite sequence. So it simply means that from some point, it will be, all the monomials will be the same. So there exists an integer k1 such that m1 of fk is equal to m1 of fk plus 1, and so on. So let me denote this monomial by m1 star. So what does it mean? It means that fk is equal c1 star m1 star plus c2 m2, etc. fk plus 1 equals c1 star m1 star plus c2 m2 k plus 1, etc. So the leading term will be exactly the same. Why? Because, well, the leading monomial must be the same because of the previous argument. But it means that we didn't reduce the leading monomial when we pass from fk to fk plus 1. So we didn't change the leading coefficient either. So the reduction happens somewhere here. So now we may consider the second leading. So if we look through the chain of polynomials here, all the leading terms here are the same. So now I want to consider the second highest term here. So I want to consider m2 of fk. It's fk1 actually. fk1, m2 of fk2, m2 of fk3, and so on. But by the previous claim, if the leading monomials are the same and we pass from one polynomial to another via the elementary reduction, then, well, these monomials are also comparable by this relation. So they are either the same or this one must be strictly smaller than this one. This is by the previous claim. That was exactly this case. And again, this is an infinite sequence of monomials. So there must be an integer k2 such that m2 of fk2 will be exactly the same as m2 of fk2 plus 1, and so on. What does it mean? It means that if I consider my sequence starting from the element k2, oh yeah, and by the way, and I want to denote this monomial by m2 star. So if I consider my sequence of polynomials starting from the step k2, I will have this picture plus c3 m3 k2 k2 plus, and so on. And after elementary reduction, I will get fk2 plus 1, and its first two terms will be exactly the same. Why? Because since the first two monomials are the same, we didn't reduce them. So we didn't touch these monomials via elementary reduction. So the reduction happens somewhere here. So these guys will be exactly the same. So and we can proceed. Yeah, and by definition, as you can see, m1 is strictly larger. M1 star is strictly larger than m2 star. So, and we can proceed. The process will never stop because we assume that we have infinite sequence of polynomials. So then, as you can see, what did we do? We have produced a monomial M1, then the monomial M2, which is strictly smaller than M1 because it's the next highest monomial in a polynomial. Then we can produce M3 on the next step. Then we will produce M4 on the next step, and so on. And we will get a strictly decreasing sequence of monomials. This is a strictly decreasing sequence of monomials. And this is a contradiction, because we already know that for monomials, every strictly decreasing sequence must stop. Okay, so let me give you an overview of what happens here. So currently, we have proven that if we take an arbitrary polynomial and an arbitrary set of non-zero polynomials, then every reduction process halts. This means that after finitely many steps, you will always get a remainder. So the only problem that the remainders could be different. So the next step is to find a way how to determine if the set G is good or not, in the sense that is it true for a specific set G that all the remainders for every polynomial f are the same or not. But this will be the topic for the next lecture, and I want to stop here. But just in case, are there any questions regarding the lecture? Yeah, and by the way, who thinks that he understood the proof of the last claim? I just want to check if there are any of you who were able to understand. Okay. That was brutal, I believe.
Oh, yes, it's more or less clear, but we are like almost dead.
Oh, but that's okay.
Not almost,
The
but
same.
completely dead.
Okay, but I believe that's just June, the beginning of the June. All the lecturers are in the same state as you. We're also almost dead. Okay, so as I can see, there are no questions. So that's simply.
I have one question.
Oh, okay, no problem.
What is remainder?
What is the remainder? It's a polynomial that is not reducible by your set G. So you cannot proceed with an elementary reduction.
Okay, could you give an example?
Okay, let me give you an example. So an example of remainder. So let's take Q of xy, and let's say x is larger than y, and we fix the lexicographical ordering with x greater than y. So if you do this reduction stuff here, you always must fix an ordering. So that's why I'm fixing an ordering. So now I can take something like x squared y plus xy squared. Let's say this will be your G. And let's say G consists of one polynomial. So what is the leading monomial here? The leading monomial is this one, and this guy is the tail. Okay? So
Okay.
this is T of G, and this is G0. Now, if you take a polynomial something like this, x cubed y plus xy, f, well, you can, there is an elementary reduction of f with respect to g, y, because this monomial is divisible by the leader.
Okay.
Okay, so this is not a reminder.
Okay.
But if you take something like this, let's say it's f1 and this one is f xy squared plus y cubed, then this guy is a remainder. Why? Because none of its monomials is divisible by the leading monomial here, because this one is not divisible by this guy, and this one is also not divisible by this guy. Well, you can actually even add something like x squared, then x squared is also not divisible by this thing. So this is a reminder.
Okay, what do we have x cubed?
Well, yeah, if we have an x cubed, then it's also a reminder, because you cannot divide it by this guy. You
Okay,
know,
so
yeah.
So it's necessary that something is divisible by the head, by the
Yeah.
leading element.
Yeah, by the head of the polynomial. Yeah.
Okay.
So if there is no monomial divisible by the leading term of the polynomial g, then it will be a remainder.
Okay, thank you.
No problem.
And one more question in the very beginning.
Okay.
The first column we had something like t, which is kind of multiplier. Why it's so important that t belongs to the set of all monomials? Why it can be contain something else? Not only xy, x1, x2, and so on, but probably xn plus 1.
You mean here?
Yeah.
Oh, because here I deal with monomials. So I know how to compare monomials. If you take t to be something like x1 plus x2, it's not a monomial, so I don't know how to compare a monomial with a polynomial.
No, I mean, yt as a monomial can contain something like xn plus 1, just another x, not from this set M.
Oh, okay. This is just the way how I think of it. So when I deal with polynomials, I prefer to fix the amount of polynomials and deal with them. When I deal with monomials, I prefer to fix the set of all monomials I deal with,
Okay.
and then work inside this set. So I just want to specify that now I want to deal with monomials in n variables. So I just don't want to deal with all other variables outside of this set.
Okay. It makes
It's
sense.
just for simplicity. It's just the way my brain works.
Okay, thank you.
No problem. Are there any other questions? Okay, since there are no questions, guys, thanks for being here, and see you next time.
Thank you.
Bye.
Thank you.